Good afternoon, everyone. Welcome. Hope you're doing well. Can you hear me okay? Awesome. Thank you. I hope your week is going well so far, and I hope you're getting through the assignments this week and getting ready for the test next Monday. So remember, we have our first exam on Monday. It's going to be exam 1, right? It's going to cover chapters 1 through 3, basically all the material that we've covered so far, plus what we're going to finish today, okay? You'll take the exam on Canvas. Remember, it's a 60-minute timed exam. You have a window between 2 p.m. and 10 p.m. to take the exam. So anytime between those two times is fine. Make sure you allow yourself enough time so that you're done by 10 p.m. because the exam will close at 10 p.m. So for example, if you have 60 minutes to take the exam, right, the latest you could start is 9 o'clock, right? If you're on DSPS and you have 90 minutes to start to take the exam, then the latest you can start is 8:30, right? Does that make sense? Also, there's a pre-exam, a pre-test for the exam. It covers the very exact same material. And that's on Mastering Chemistry right now. And you could take that anytime between now and next Monday. That is not timed. And it's like a normal Mastering Chemistry assignments where you can have multiple attempts, right? And that's designed to help you to learn the material, okay? Remember, for the exam, you can use the equation sheet I sent you, sorry, the constant sheet I sent you, the periodic table, and then one notebook size sheet of information you can write whatever you want on, okay? And then a calculator and a pencil or pen and scratch paper, obviously, so you can work out your problems. We have a little bit of material left to cover today, so I'd like to get started on that pretty soon, but I want to make sure I want to see if there are any questions. Are there any questions from anyone? Yeah, Megan.
I don't know if you plan on doing this in just a second, but could we go over with finding the empirical formula, how you know to multiply by a certain number?
Great question. That's the first thing we're going to do today. So we're going to get right on that first thing. Thanks for asking. Nayeli.
Hi, so I realized that for the periodic table that we're given, it doesn't have any of like the names of the elements. So would we be able to like have another periodic table with like the names in case we need them for naming?
No, if you want to though, on your cheat sheet, you can write down the names of those that are a little weird.
Got it. Thank you.
Anything else? Okay, very good. Let's go ahead and get started. Remember, there's lots of tutoring available from now until Friday, right? So if you need help on the problem set or studying for the exam, there's lots of tutoring available at all these times. I am also going to have an optional Zoom session on Monday before the exam in case there's any last minute questions. Okay, so optional Zoom Monday from 1 to 2 p.m. Okay, so I'll just be hanging out on Zoom at that time. That's the hour before the exam. And if you have any last minute questions, right, you can just see me then. Obviously, you can email me. During the exam also, I will be monitoring my email pretty diligently in case anything comes up, okay? All right. Let's go ahead and get started then with today's information. What I'm going to do today is cover the last couple topics that we need to cover for the exam, and then I'd like to do a quick review of the information that you need to know for the exam. Okay, so let's start with getting the molecular formula from the empirical formula and the molar mass. So we just spent a lot of time learning how to get an empirical formula, right, from experimental data. Right? So for example, if you have the masses of the elements that are present in the compound, right? Or if you have the percent by mass of the elements in the compound, right? You can go through that procedure, right? And you can get the empirical formula, okay? Remember, the empirical formula is not the molecular formula necessarily. For some compounds are the same, but certainly not generally true, right? So remember that the empirical formula is always, the molecular formula is always some integral multiple of the empirical formula, right? So the empirical formula times some integer n always gives you the molecular formula, right? So for example, if you have something like, let's say C3H6 as your molecular formula, right? The empirical formula is C1H3, right? And what would N be in that case? What would this N be that you would multiply the empirical formula by? Did I mess that up? C1H, yeah, I did. What would N be?
3.
3, yeah, it'd be 3, right? You'd multiply it by 3, and that would give you C3H6, right? So N is just that number that you multiply the empirical formula by to get the molecular formula. Okay, let's do an example. So if you know that you have a compound, in this case, benzopyrene, and it has a molar mass equal to 252 grams per mole, okay? So you know its molar mass, and you know its empirical formula equals C5H3, right? And you want to try to get its, want to try to find the molecular formula. And you're given, right, the molar mass, and you're also given the molar masses of the elements that compose it, right? So again, remember that the molecular formula is going to be equal to n, some integer, times the empirical formula, right? So you have to figure out what that integer is. What is n, right? And so how are you going to do that? Well, you're given the molar mass, right? So you can figure out, oh, okay, well, what is the empirical formula molar mass? And then you can compare the two, right? And that'll give you what n is, right? So the empirical formula molar mass, in other words, the molar mass of this thing right there, right, is equal to 5 times 12.01, right? 5 times carbon plus 3 times hydrogen, 1.01, right? And that gives you 63.08, right, grams per mole. Okay, so that's the empirical formula molar mass. So then n is going to be equal to the empirical, to the molar mass, divided by the empirical formula molar mass, right? That gives you that integer n, right? So in this case, we just plug those in. The molar mass, right, we're given up here. So we just put that there. The empirical formula molar mass we just calculated, so we put that there, right? And we get 252 grams per mole divided by 63.08 grams per mole, right? And that gives us basically the integer 4, right? So 4 is the integer that we have to multiply this by to get the molecular formula, right? So molecular formula is equal to 4 times C5H3, right? And that gives us C20H12. And that's how you get the molecular formula from the empirical formula. Does that make sense? Okay, let's have you try it. Go ahead and try this yourself. Same kind of question, right? You're given the empirical formula, and you're given the molar mass, and you got to find the molecular formula. So go ahead and try that. Okay, try to finish up that in the next 10 seconds or so. Okay, nice. Virtually all of you got that. The right answer is D, right? And so you can see 93% of you got that. Very, very good. Real quickly, you just got to find N, right? So the way you find N is you take 42.08, right? The given molar mass and divided by 14.03, which is the empirical formula molar mass, and that gives you 3, right? So CH2 times 3 gives you C3H6, and that's your molecular formula. Okay? Does that make sense to everybody? Okay, awesome. Very, very good. Let's move on. So we've learned how to get an empirical formula, right, from experimental data. And so far, the kind of experimental data we've looked at is either the masses of the individual elements in the compound, right, or the percent by mass, right? And we went through that procedure where we assumed 100 grams and got the moles, right, and wrote a pseudo formula and all of that, right? So there's yet one more way that I want you to know how to get an empirical formula from experimental data, and that's by something called combustion analysis. So this is a very common way to figure out empirical formulas for compounds. You essentially burn the compound in oxygen, this works really well with organic compounds, and we'll talk about organic compounds in a minute, but basically organic compounds contain carbon, hydrogen, and usually some other, and then sometimes additional elements like oxygen or sulfur, okay? So you burn it, and then you look at what is formed when you burn it, right? And you look at how much water is formed, and you look at how much CO2 is formed, okay? So this allows you to basically take a compound that contains carbon and hydrogen and maybe some other elements, right? And then you burn it, right? You combust it, and you get CO2 and water. And from that data, then we can get to the empirical formula for the compound, okay? That's what we want to try to get to, okay? So let's look at the procedure. Here's the procedure for combustion analysis. And this procedure is just one you're going to have to know how to do, all right? Just like the procedure for percent, when I give you percentages of the different elements in the compound, you know how to go through those steps to get to the empirical formula. Same thing here, all right? This is just a little bit different. There are some similar things, but there's also a couple of differences, all right? So in combustion analysis, you write down as given the masses of each product, right? And then you convert them to moles, right? And then you do a couple other steps where you end up writing down a pseudo formula just like we did before, and you divide by the smallest just like we did before, and then you get the empirical formula from that, okay? So let me just show you an example. I think that'll be the easiest way to see how this works, okay? So let's write down what we're given here. We're given that we have 0.844 grams of the sample. I'm just going to call it Ca for caproic acid. And we're given that it contains only carbon, hydrogen, and oxygen. Okay, so those are the three elements that it contains, right? So basically what we got to do from this data is figure out, okay, how many moles of each of those three elements are there so we can write down our pseudo formula, right? That's the idea, all right? And it says that when you burn it, right? When you burn it, you form 0.784 grams of water, right? And you form 1.92 grams of carbon dioxide. And you're asked to find the empirical formula, okay? And you're given the atomic masses of carbon, hydrogen, and oxygen. Okay, so let's go down to this procedure and let's go through it step by step, okay? This is a little bit complicated, so you really have to kind of take this kind of problem slowly and go through each of these steps very carefully. Make sure you write everything down, right? And be able to go back and check your work for mistakes, right? 'Cause it's easy to make a mistake in this procedure. Okay, so we already did step number 1 here, right? We wrote down as given the masses, right? Step number 2, and I'm gonna go ahead and combine steps 2 and 3 here all into one step. Steps 2 and 3, we're gonna convert the masses of CO2 and water to moles. And then we're going to convert the moles of CO2 and moles of H2O to moles of carbon and moles of hydrogen. All right, so here I'm trying to figure out, in these 2 steps, I'm trying to figure out, okay, how many moles of carbon and hydrogen, right, do I have in this compound? Okay, so I'm going to start with my grams of CO2, 1.92 grams of CO2, and I'm going to convert that to moles of CO2. 1 mole over 44.01 grams. This is just the molar mass of CO2 right there, okay? And then I'm gonna convert, notice I wanna get to moles of carbon, all right? So what's my conversion factor that takes me from moles of CO2 to moles of carbon?
The molar mass?
No. Remember we learned this last time, right? Inherent in this formula is the conversion factor between moles of carbon and moles of CO2, right?
Is it 1 mole of carbon dioxide and then above that 1 mole of carbon?
Exactly right. 1 mole carbon, 1 mole carbon dioxide, right? Because you know from the formula that you have 1 mole of carbon for every 1 mole of carbon dioxide, right? So my moles of carbon dioxide cancel, right? And I end up with moles of carbon, and that comes out to be 0.0436 moles of carbon. Does that make sense, everyone?
Yes.
Yes, yes, no, maybe so. All right.
Are we going to do the example?
We're doing an example, yeah. Yeah, we're doing this example right here, right? So we got moles of carbon. The next step is to get moles of hydrogen, right? And we're going to get that from the amount of water that we were given, right? So we're going to write 0.784 grams of water, right? Times 1 mole over 18.02 grams. And that's going to give me moles of water, right? Now, what's my conversion factor to get to moles of hydrogen?
Would it be 2 moles of hydrogen over 1 mole of water?
Correct. 2 moles hydrogen over 1 mole of water. And again, how do we know that? From the chemical formula, right? We know from the chemical formula that each mole of water contains 2 moles of hydrogen. Okay? So the moles of water cancel, and I'm left with moles of hydrogen, and I get 0.00870 moles of hydrogen. Clear enough so far? Now, so those are steps 2 and 3. Now step 4 says if the compound contains an element other than carbon and hydrogen, then it tells you how to find the moles of that other element, right? If this compound only contained carbon and hydrogen, then we could go right to step 5. We could write down a pseudo formula using these moles, just like we did with all the other problems, right? Okay. So these kinds of problems could either be a little simpler if it's only carbon and hydrogen, in which case you go straight from here to the pseudo formula. Or they could be a little more complicated where there's some other element involved. Like in this case, there's oxygen involved. Okay. Now, here's the problem. The oxygen that is in the CO2 and water, right? This oxygen and this oxygen here doesn't come only from the compound. It comes also from the combustion process itself. Okay, so in combustion, you add oxygen, right? And so some of the oxygen here and here comes not just from the compound, but from that oxygen that it was burned in. Okay. Let's see. Did I write this down? 0.0870. Thank you. This I have too many zeros here. Okay. Thanks for catching that. Appreciate it. All right. So in this case, we gotta go through this other step. So step 4 here. Step 4 says the compound contains an element other than carbon and hydrogen, which in this case it does, right? Because it has oxygen. Find the mass of the other element by subtracting the sum of the masses of carbon and hydrogen from the mass of the sample. Well, here's the mass of the sample, right? We're given that. We have moles of carbon and hydrogen, right? So we can find from moles of carbon and hydrogen, we can get grams of carbon and hydrogen, right? So the grams of carbon and hydrogen are going to be 0.0436 moles of carbon times 12.01 grams per mole. And that's going to give me 0.524 grams of carbon.
No, you're fine.
Okay. Let's see. No questions. Okay. And then grams of hydrogen from the moles of hydrogen, then 0.0870 moles of hydrogen, right? Times 1.008 grams per mole. That cancels, and that gives me my grams of hydrogen, 0.0877 grams of hydrogen. Okay. So notice this was moles of carbon hydrogen here. This is grams of carbon hydrogen here. And the only reason I'm calculating this is so I can somehow figure out my grams of oxygen, right? I'm still trying to figure out how many grams of oxygen I have. So how am I going to do that? I'm going to take the mass of the compound, which includes the carbon, hydrogen, and oxygen, and subtract out the grams of carbon and grams of hydrogen, right? So the difference between those two masses should be the mass of what?
Oxygen.
Correct. Correct. Exactly right. Okay. So grams of oxygen, right, is going to be equal to 0.844 grams of the compound, right? That's this number right there. I'm just going to write that number, right? Minus, right, the carbon and the hydrogen. Here's my carbon. Here's my hydrogen. So I'm going to subtract out those. 0.524 grams plus 0.0877 grams, right? And that ends up giving me 0.232 grams of oxygen. Okay? The next step then is to say, okay, now I know grams of oxygen, but really what I need is moles of oxygen, right? So how do I get from grams of oxygen to moles of oxygen?
Avogadro's number.
Not Avogadro's number, just from grams to moles.
Molar mass.
Molar mass, correct. So I'm going to say 0.232 grams of oxygen times 1 mole over 16.00 grams. And that's going to cancel, and that's going to give me 0.0145 moles of oxygen. Right? So now look what I have. I have moles of carbon, right? I have moles of hydrogen, right? And I have moles of oxygen, okay? So now I can do step 5 here and write down a pseudo formula, right? And now we're just back to where we were before when we've done these kinds of problems where we write down a pseudo formula and then divide by the smallest number, right? So our pseudo formula is going to be what? Carbon 0.0436, right? This number right there, all right? Hydrogen 0.0870, right? And then oxygen 0.0145. You with me? Questions so far? Okay, so the next step is to divide all the subscripts by the smallest one, right? So the smallest one here is going to be 0.0145. Right? And I'm going to get C3H6O. And then, so because that all has whole numbers, I don't have to multiply by anything, right? That is my empirical formula. So that's my answer. Okay. Does that make sense?
Wait, quick question.
Yeah.
Sorry. After you compute the mass or the grams for both, I think, carbon and hydrogen, what is the next step that you do?
Yeah. Okay. So then, so remember, ultimately, we're after like the moles of each of these 3 components, right? Because we want to know what are the moles of carbon, moles of hydrogen, moles of oxygen. Why do we want that? So we can write the pseudo formula, right?
Right.
First step, in this step right here, right? We got the moles of carbon and hydrogen from what? The moles of carbon dioxide and the moles of water. Because all the carbon that was in the compound went to carbon dioxide. All the hydrogen that was in the compound turned into water when we underwent combustion, right? So those 2 were pretty easy to get. It's those moles of oxygen that are difficult, right? Because even though there's oxygen here and here, that oxygen came from two different sources. It came from the compound, but it also came from air. So you can't use those number of moles to get the moles of oxygen. The only thing you can do is you say, okay, well, I know that the mass of the sample, right? And I know the mass of two of its components, right?
Mm-hmm.
So if I subtract the mass of the sample from the mass of the two components, then that must be the mass of that extra component, oxygen.
Okay.
Does that make sense? So that's what I'm trying to do here. I'm saying, okay, I have 0.844 grams of the compound, right? That contains carbon, hydrogen, oxygen. Then I figured out this is how much carbon and this is how much hydrogen. So I subtract that away, and that is the grams of oxygen then that's left over.
Okay. Can you briefly go back to the original question, maybe?
Sure.
Okay.
Yeah, so you're given all that information, right? You're given, this is all the stuff that I wrote down here from the problem.
Produced.
All right. So
Okay.
I'm going to give you a chance to work one of these.
I actually have a question about this.
Yeah.
Is the other element always going to be oxygen since it's combustion, or
It could be other elements as well, like sulfur or nitrogen, but you would do exactly the same thing.
okay?
You get the mass of the other element by finding out the carbon and the hydrogen and then subtracting out that from the total mass of the compound.
Okay.
But oxygen is going to be the most common. Okay. Are you ready to try this? I'm going to go ahead and start this poll. I'm going to let you see the question. And then because there's a little bit of a long problem and because you might get stuck, I'm going to try, let me see if this works. I'm going to try putting you guys in breakout rooms so you can talk to each other. And let's see, if I do 26, there'll be 2 or 3 people per room. So I'm going to try this, and you can talk to other people in your room and work through this together. Okay. So let's try it. Go ahead and join the breakout room.
When we go to the breakout rooms, we can't see the equation.
Okay. You can't see this right here.
When we go to, well, now I can see it because I left my breakout room.
Okay, I didn't realize that. So, okay, let's see.
Thanks to write it.
You didn't get a chance to see that, right? You didn't get a chance to see the.
No, I just left.
What's that? Okay, this didn't work out. Okay, that's okay. I'm going to.
Could you just do you know the formula? Like I got the combustion of 3.6.
Yeah, let me stop the breakout rooms and then I'll let you read the question and then we'll go back to them. Okay.
Okay. Thank
Okay.
you.
Okay. Let me do that. I think that's the best idea. Okay, so breakout room.
Can you put the question up again, please?
That's what he was gonna do, but where is he? I don't think he's here, is he?
I think he's trying to break all of the other rooms. That's why.
Yeah.
So I think for now we just have to wait for him, basically.
You're still muted.
Professor, you're muted. Nope.
Is he here?
Does anyone have the problem?
Here, Professor, you're muted though. No one can hear you.
Yes. Nobody can hear you, Professor.
My God. Just.
Oh. This is funny.
Also, has anyone told him that? Were you guys able to see the question in the breakout room? Because I
No, I couldn't. I didn't. Yeah.
Oh.
No, he did.
Oh,
there we go.
Still can't.
Hello.
Wait.
Now my poll disappeared.
Oh,
it's just in the background somewhere.
Really? Mine is still here.
I still can't hear him.
You can unmute yourself.
The polls, when you minimize the polls, they show up between participants and chat. There should be a little button that says polls.
Yeah, there should be. It should say mute or stop video.
Oh.
Stop the poll.
It's the very bottom of the Zoom document, I think. On mine, it's like the far left icon.
In the chat, Professor, you're muted.
I wonder if he can hear. I wonder if he can hear us.
Check your microphone source.
I think he can.
Check your microphone source.
Is he not in the breakout room?
He says that he can hear us. He's giving us a thumbs up.
Okay.
There you go.
Yay! That was a bad idea.
There we go.
That was a really bad idea. Okay, we are going to start over.
Can you walk us through this one?
Yeah, I can walk you through it. I'm going to give you a minute to think about it because I think it'll be more helpful if you think about it just on your own for a minute, and then I'll walk you through it. Okay.
Thank you.
Can you see my screen? Can you see my screen?
Yeah.
Yeah.
Okay.
Yes, we can see your screen.
Perfect. All right. So go ahead and try working this problem. Yeah?
Yes.
No breakout room. Thought that would work, but didn't work, obviously.
So it is going to be
Gabby, you want to mute yourself?
Sorry, I'm sorry.
Are you going to put up the poll again?
Yeah, thank you. Okay. So if you're not here yet, remember the first step is to figure out the moles of carbon and hydrogen from the moles of carbon dioxide and the moles, from the grams of carbon dioxide and the grams of water.
The mass of all the elements present.
Pardon me?
To find the mass of the present elements.
You go from moles of each of the carbon and hydrogen to grams of carbon and hydrogen.
Okay.
Okay, so I'm gonna just work it concurrently with you in case you're stuck. Some of you might be past this stage already, but the first step is to figure out the moles of carbon and the moles of hydrogen, right? And how do you do that? From the grams of carbon dioxide and the grams of water, right? So you go from grams of carbon dioxide to moles of carbon dioxide, then use the mole ratio from the formula, and that gives you moles of carbon, right? And then you go from grams of water to moles of water, and then the mole ratio to get to moles of hydrogen. Okay, that's the first step. The next step is to use those to get to grams of carbon and hydrogen. Okay, so go ahead and start that step if you haven't already. All right, so notice in the second part, what I did is in this first part, I got moles of carbon and hydrogen. In the second part, I got grams of carbon and hydrogen. And why am I doing that? The only reason I'm doing that is because I need to get to moles of oxygen. And the only way I can get moles of oxygen is by figuring out the mass of everything but oxygen in the compound, right? So now I know that this is the mass of everything but oxygen. I'm given the mass of the compound, right? 3.69 grams. So now the grams of oxygen, right, is going to be equal to the mass of the compound, 3.69 grams, right, minus the sum of these two masses, right, 1.477 grams plus 0.249 grams, right? And that's going to give me the grams of oxygen, which is 1.96 grams. All right, now notice what I have so far, right? I have moles of carbon, I have moles of hydrogen, but for oxygen I only have grams, so but what do I really need? I need what?
Moles.
Moles, right? So now what I got to do is convert from grams to moles, right? 1.96 grams of oxygen, so this is going to be moles of oxygen is 1.96 grams times 1 mole over 16.00 grams. And that's going to cancel.
We can't see what you're writing.
Thank you. And that's going to be equal to 0.123 moles of oxygen. Okay, so now we know the moles of carbon, moles of hydrogen, moles of oxygen, right? What's the next step?
Get the empirical formula.
Right. You write the pseudo formula. So go ahead,
Oh, yeah.
go ahead and try that step yourself. Hey, Yoon, I'll get to your question in just a minute.
So we should be rounding it to 3 decimal places, like in the middle of the question?
Yeah, you can, you know, on these kinds of problems, you can round it to, yeah, you can round this to 3 decimal places. That's not a problem. Yeah. Okay. Because in the end, you're looking for it's going to be round numbers anyway. So on this kind of question, you know, you would just keep everything. The significant figures aren't as important as in questions where you're actually looking for a numeric answer that has, you know, several significant figures. In this case, you're going to round everything to the nearest one anyway, right? So it's not as important.
Okay, thank you.
Yeah. Okay, so in the last step here, you write your pseudo formula, and then you divide through by the smallest number, right? And when you do that, you end up with this, which is your empirical formula. All right. Okay, so that's a complicated problem, right? But you're going to have to know how to do this for the exam. Okay, you're going to get more practice in the post-lecture video today. All right, that you're going to do, and you're going to get more practice at working these kinds of problems. But this is absolutely, you have to know how to do this kind of problem for the exam. Okay. Let's see. I'm going to go ahead and give you the answer. It is E, right? And I'm going to end the polling. Most of you that got there got E, so nice work. All right. See here, most of you got E, so that's great.
I have a question.
Yeah.
So for the carbon, let me see. Didn't you get, for your grams of carbon, didn't you get 1.471? So shouldn't it be?
Right, but remember that this is moles of carbon, not grams of carbon, right?
Okay, got it, yeah.
Right, this is moles. So the only reason you're getting grams here, right, is why, so you can figure out your grams of oxygen here. All right, for the formula, what you really need is moles, right? You need moles. The formulas are always moles. The only reason you're getting grams here is you can subtract out from the total mass of the compound so you can get your mass of oxygen.
Okay, got it.
Does
Thank
that make
you.
sense?
Yeah.
I also have a question.
Yeah.
It's about the order in the compound. So why is it that C is before the H? I don't know which is more closer to the to the metals in this case.
Yeah, I know that's hard. So just by convention, carbon is always written first in these compounds, in these organic compounds.
Okay.
So don't worry too much about that. If you make a mistake there, that'd be fine. That's not that big a deal. But over time, you'll get used to just seeing it this way. These are the way these are written.
Okay, thank you.
Yeah, that's a great question. Okay, we need to move on. So I'm gonna move on. I have one more little topic that I'm gonna cover, and then I'm gonna do a quick review. Okay. My last topic is this idea of organic compounds, and so organic compounds are a class of chemical compounds. All right, it's a very important class. In fact, next year, many of you will take a full year of organic chemistry where you study this class of compounds and only this class of compounds, all right? So to give you an idea of organic compounds and how they were sort of thought of, a couple hundred years ago, chemists sort of separated all compounds into 2 different classes, organic and inorganic, all right? And at that time, organic compounds came from living things. And inorganic compounds came from the earth. So a good example of an organic and inorganic compound would be sugar and salt, okay? Where does sugar come from?
A plant.
A plant, yeah, from sugar cane or sugar beets, right? So it comes from a living thing. So we would classify sugar, right, as an organic compound. Where does salt come from?
Mineral.
Mineral, and you can get it from the ocean or you can get it from mines, right? So that comes from the earth. So that's an example of an inorganic compound. The organic compounds were seen to be fragile, okay? What do I mean by that? Whereas the inorganic compounds were more durable. Again, what do I mean by that? What happens if you put sugar in a pan and heat it over the oven? Heat it over your stove.
It'll melt.
It burns.
It burns. Or actually, it does. If you're really careful, you can caramelize it, right? If you're a chef, right, and you're really careful, you can caramelize the sugar, right? But normally, if you're just a deadbeat like me, you turn on the fire, and eventually it starts turning black, and it smokes, right? And what's happening? The sugar is decomposing. What's it decomposing into? Carbon and water and perhaps a few other substances, right? But it's decomposing. Why? Because sugar is organic. Organic compounds tend to be fragile this way, right? What happens if you take a bunch of salt and put it in a pan and put it over your stove?
Nothing. Stay solid.
Nothing happens, right? It's durable. You can heat it up to hundreds of degrees, and there it is, hot salt, right? That's what you have, yeah? So salt is an example of an inorganic compound, comes from the earth, tends to be fairly durable, right? Not easy to decompose. Sugar, on the other hand, comes from living things. It's an example of an organic compound. It's more fragile, right? More easily decomposed, all right? So we had this kind of big divide in chemistry 200 or 300 years ago, where we really divided compounds into organic and inorganic. And then to top it off, chemists were able to synthesize inorganic compounds in the lab, but they were not able to synthesize organic compounds. All right. In other words, if I put sodium and chlorine together, elemental sodium and chlorine together, big reaction happens, sparks fly, and I get sodium chloride, right? I get salt. If I take the elements that are in sugar, carbon, hydrogen, and oxygen, and I put them together, nothing happens. All right. You can't really synthesize sugar very easily. And at that time, they couldn't synthesize it at all, right? So organic compounds could not be synthesized in the lab, but inorganic compounds could. So there existed this huge divide between the two, okay? That all changed in 1828. There was a chemist, German chemist by the name of Wohler, and he was the first one to synthesize an organic compound in the lab. All right, no one had done that until that time. So before that time, organic compounds were seen to have like this kind of, living things were seen to have this sort of mystical quality. It was often called the vital force. Or let me define it this way. Let me define vitalism. Vitalism, the belief that living things had a vital force that allowed them to make organic compounds, right? So if you wanted to make sugar, right, the only way you can do that is in the sugar cane or a sugar beet, right? Why? Because living things have this vital force, right? And that vital force was sort of this mystical thing that allowed them to synthesize organic compounds. In the lab, you couldn't make organic compounds, right? The reason I'm bringing this up is because this was a huge change in science, right? When this happened, the significance of that, we're still experiencing the significance of that today, right? Why? Because before this time, right, you had this big divide, right? You had living things, which had this sort of magical property, right? This vital force, and non-living things, which we could study and understand. But what happened in 1828? For the first time, we were able to synthesize an organic compound in the lab. And that opened up a whole range of things to scientific study that we're still doing today. So today we can synthesize hundreds of thousands of organic compounds, hundreds of thousands of drugs, right? We can understand living things not as if they have something that's ununderstandable, but rather we can understand them sort of from the same molecular point of view that we understand salt, right? Living things are much more complicated, obviously, right? But the biggest growth in science, arguably in the last 50 years, has been in this area of applying chemical principles to living things, right? All the way to where we now know the human genome, for example. We know the sequence of genes in humans, right? That end up being the instructions to synthesize all the proteins that make us up, right? So what happened in 1828 was very significant because of that. It opened up a flood of scientific advances that continue to this day. All right, anyway, just wanted to get that across. Let me just talk a little bit more about organic compounds and then we'll do a review. So organic compounds today are really defined in terms of their composition, right? They contain carbon, hydrogen, and a few other elements. Namely things like oxygen, sulfur, nitrogen, phosphorus, right? Those are the main ones. But carbon is the star, right? Carbon is kind of the king of organic chemistry. And so here's sort of the simplest carbon compound that contains hydrogen. This is methane. This is what we burn in our stove. It's the main component of natural gas, right? And here's the structural formula, and there's the space-filling model. Carbon is unique because it can bond in a lot of different ways, right? So if you look at the periodic table and you think, okay, let's just think about all the compounds that exist. Carbon forms more compounds, right, than all of the other elements in the periodic table do, right? So carbon has this diversity of chemistry that it can do, right? And part of it is because it can bond in so many different ways. It can form double bonds. It can bond to itself, right? It can bond to other elements. It can make chains. It can make branch structures. It can make rings, right? All this possible diversity, right? Which is why organic chemistry is basically the backbone of living things, right? Most of the compounds in our bodies are organic compounds, all right? I'm not going to really worry about that. Let me just show you some common hydrocarbons. Hydrocarbons are organic compounds that contain only hydrogen and carbon. Organic compounds that contain only carbon and hydrogen, okay? So here's some of them: methane, propane. Some of these might sound familiar. Where do you find propane?
On a camping stove.
Pardon me?
For camping stove?
Yeah, exactly. You use it for fuel, right? Like in your backyard grill, right? And for camping stoves. Butane is another example. This has 4 carbon atoms. Pentane is found in gasoline. Ethene is a ripening agent in fruit, right? This is given off by bananas that help clusters ripen, right? So organic compounds are super important in most of the foods we eat. Most of the things we smell are organic compounds, all right? And I wish we had more time to go into them, but we really don't. So I'm going to stop right there in terms of the material for the exam. So you can put a big line in your notes and say, exam 1 here, okay? Because this is the end of the material for the first exam, okay? All right, so what I want to do really quick, and I know we're running a little short on time, but I want to be able to review for the first exam here, okay? Can everyone see my screen and hear me? All right, so the exam will cover chapters 1, 2, and 3, right? Beginning with chapter 1, we talked about atoms and molecules, right? So I expect you to know about those, and of course we've been talking about those ever since, so you have quite an introduction. The scientific approach to knowledge, right? What's the difference between an observation, a law, a theory or model, and experiments, and what role does experiments play, right? Scientific approach to knowledge, make sure you understand that. The classification of matter, we talked about the classification of matter according to its state, right? Solid, liquid, or gas. And we also talked about the classification of matter according to its composition, right? Is it a pure substance? Is it a mixture? If it's a mixture, is it an element, or is it a homogeneous mixture or a heterogeneous mixture? If it's a pure substance, is it an element or a compound, right? The classification of matter, kind of the first, we need to understand that so we can begin to understand matter from the particulate point of view. Right, we talked about the properties of matter, so know the difference between, for example, physical properties and chemical properties, right? We also talked about chemical change and physical change, right? So make sure you understand that. We talked about energy just briefly, right? Just a little bit. So the units of energy, joules, the law of conservation of energy, right? Energy is neither created nor destroyed. And then we define different types of energy like potential energy and chemical energy and kinetic energy, right? So know all of that. The units of measurement, we talked a bit about units of measurement and using scientific notation and using prefix multipliers, right? And then we also talked a lot about significant figures, right? So know how to work with significant figures and do calculations to the correct number of significant figures, okay? These are the main concepts that were in chapter 1. And then there's a bunch of skills that I sort of expect you to know from chapter 1. This is just the table from your book, okay, from the end of chapter 1, so you can find this in your ebook. And it lists sort of the main skills that you should be able to do if you understand the material in that chapter, right? So you should be able to apply the scientific approach to knowledge, right? Classify matter according to its composition. And by the way, this little table over here also has exercises in the end of the chapter where you can practice those skills. It also has examples. It also tells the number of examples in the book where you can practice those skills. And these 4 practice problems in the book are really good practice for the exam, right? Because if you can do these 4 practice problems, if you can do all of these listed here, you should be able to do all the problems on the exam as well, okay? All right, compare Fahrenheit, Celsius, and Kelvin temperature scales, be able to convert back and forth between those, right? Express measurements using prefix multipliers, right? So things like millimeter, centimeter, right? Be able to work with those prefix multipliers. Again, remember, you don't have to memorize them because you're going to have your conversion sheet with you, right? But you just need to know how to work with them. Density, know what density is and be able to use it in calculations, right? Determine the number of significant figures in a measurement. And then work with significant figures when you're doing multiplication, division, addition, subtraction, right? And then unit conversions, and then solving problems, right? Those are the skills that we sort of learned in chapter 1. The important equations from chapter 1 are also at the end of the chapter, and these you'll have to know or write on your cheat sheet, right? Remember, everyone gets a 1-page cheat sheet that you can fill up with as much information as you want, right? So the conversions between Kelvin and Celsius and Kelvin, Celsius and Fahrenheit, and then the equation for density, okay? Let's see, I think I'm gonna hold off on questions till I finish all of this, Skylar, only because we only have about 14 more minutes and I have 2 more chapters of review I need to get through. So I'm going to hold off on questions and I'll take questions at the end. Chapter 2. So remember chapter 1, right? We was sort of about some basic things, right? Atoms and molecules, just understanding matter, understanding energy, understanding units. Chapter 2, on the other hand, now focuses on atoms and elements, right? Atoms and elements. So we learned about the atomic theory, right? The idea that matter is made of atoms. Then we learned that the atom itself had parts, right? It had electrons, protons, and neutrons, right? People discovered the electron. And then we learned a model for the atom called the nuclear atom that came from Rutherford's experiment, right? And then we learned about the subatomic particles, protons and neutrons, right, that make up the nucleus, okay? The periodic table, right? I want you to be familiar with the periodic table and know your way around it. Know the major classifications, right? So know the difference between main group elements, for example, and transition elements. Know those families that we talked about, like the alkaline metals and the alkaline earth metals and the halogens, right? Then we also talked about atomic mass. So be able to know how to find atomic mass and especially be able to work with it and apply it to the mole concept, which was the last thing we learned in chapter 2, okay? Again, here's sort of the skills for that chapter, right? Apply the mass laws that are the basis of modern atomic theory. So by this, I mean the laws of constant composition and the law of conservation of mass, right? So make sure you understand those laws and how they apply to the atomic theory. And for the experiments, I want you to know the basic details of each experiment. You don't have to know any dates. There's nothing that's going to be like, what date did this happen? But the scientists and their experiments and why they were important, right? Then the structure of the atom, right, in terms of the nuclear model. The properties of subatomic particles. By this, I mean, you know, that protons are positive, neutrons are neutral, electrons are negative, right? And that protons and neutrons have masses that are very similar to each other, and that electrons have a mass that's much, much lighter than either of those two particles and is negatively charged. All right, be able to interpret isotope symbols, right? So when you write those symbols that have the symbol for the element and then the mass number and the atomic number, make sure you know how to interpret those. Relate the periodic law to the organization of the periodic table, right? So understand what the periodic law is and how that led to the periodic table. Be able to predict the charge of those common ions that always form the same charge, right? Be able to determine the atomic mass of atoms, so know the formula for finding the atomic mass from the different isotopes and their abundances, and I'll show you that formula here in a minute. And then apply the mole concept again, this time not to just elements, but to compounds, okay? So here is the formula for atomic mass, right? Where you sum up each isotope times its fraction, right? To get the atomic mass. And then the relationship between the mass number, A, which is just equal to number of protons plus number of neutrons. All right, and again, all of this information, this table and these equations, you can find at the end of every chapter in your ebook, or if you have the printed book, at the end of every chapter in the printed book. Okay. All right, chapter 3, we talked about chemical bonds, right? Especially one of the main things you need to be able to do is distinguish between those compounds that have ionic bonds and those that have covalent bonds, right? Ionically bonded compounds are called ionic compounds, and covalently bonded compounds are called molecular compounds, all right? So make sure you know how to do that. Chemical formulas, right? Know what a chemical formula is. Know the difference between the different types of chemical formulas that we talked about, right? Ionic and molecular compounds, know the difference between those. Atomic and molecular elements. So I want you to know which elements are molecular, and the ones that are molecular, remember, are that basically the halogens, right? Chlorine, bromine, iodine, and so on. Oxygen, nitrogen, and hydrogen, right? And those are all molecular elements that exist as diatomic molecules, not as individual atoms. Okay, all the nomenclature stuff, make sure you know how to name ionic compounds, molecular compounds, and acids, right? I encourage you to use that flow chart that we used in class that you can also find in your book, all right, to be able to name these. Formula mass and the mole concept for compounds. Again, be able to figure out the formula mass for compounds where you add up the atomic masses of each of the individual elements, right? And then be able to apply that mole concept so you can figure out conversions between grams and moles of compounds and grams and number of molecules and that sort of thing. Chemical composition. So we talked about percent composition. So be able to, if you know the formula of a compound, be able to figure out the percent composition by mass of any of its elements, right? And be able to use that as a conversion factor in calculations. And then also, we learn how to determine chemical formulas from experimental data. 3 different kinds of data you might be given. You might be given the masses of the elements in the compound. You might be given the percentages of the masses of the elements in the compound. Or you may be given the results of combustion analysis. From any of these 3, you should be able to work through the steps to get to the formula, the empirical formula of the compound. All right, and then just real briefly, organic compounds, what are they and what makes them different, or how are they defined? All right, chapter 3, skills. Be able to identify substances by the type of bond they form, covalent or ionic, right? Be able to write formulas and names for ionic compounds. Be able to write formulas and names for molecular compounds, right? So in other words, I want you to be able to go from the name to the formula or from the formula to the name, right? Either direction on both of these. Same thing for acids and oxyacids, formulas and names, right? Then analyze the composition of compounds in terms of formula, mass, mass percent, and moles. So here, this is what this is where you can find the percent composition of a compound from its formula, right? Then also be able to write chemical formulas from experimental data. And experimental data would be these 3, given masses, percentages, or combustion analysis. And then lastly, you don't have to write formulas and names for organic compounds. You just have to know what they are, okay? Just know what they are, be able to recognize an organic compound. That's all I really need you to know about organic compounds for right now. Equations, the formula for calculating formula mass, right? So how do you figure out formula mass for a compound? You just sum up the atomic masses of the different elements, right? Times how many atoms of that element. The definition of mass percent composition. And then lastly, how to get the molecular formula from the empirical formula. You got to figure out this integer n, right? And n you can get if you know the molar mass and the empirical formula molar mass. Okay. So I know that was pretty fast. This, of course, will be recorded and you can go back and review it at your leisure. But that kind of tells you all the material that will be covered on the exam. All right. Okay, we have 5 minutes, so I can take some questions. Let's see, Abe.
Yeah, so when we're going to looking at like covalent bonds, like when we're like deciding which I guess compound forms those bond types, is that what you're asking?
Yep.
Okay.
Yeah.
And then you would just decide that through the electrons, right?
Well, you look at if it's a metal and a non-metal, what kind of compound is it?
It'd be ionic.
Correct, right? So
Okay.
if you have something like, calcium chloride, right? Metal,
Yeah.
non-metal, so that's ionic. But if you have carbon tetrachloride, non-metal, then that's molecular.
Molecular meaning like covalent as well?
Correct. So
Okay.
a molecular compound contains covalent bonds. An ionic compound contains ionic bonds.
Okay. And we don't have to know like the different types of covalent bonds yet, right?
Correct.
Okay.
Emmanuel.
My question is just, I mean, obviously all this information is important, but where would you say we would need to focus at, like our main energy, so that way we can be efficient on this exam?
Yeah, so I think a good way to study for this exam is, first of all, to review your lecture notes. Okay, so you get a good general picture of where you are. But after that, the main thing to do is practice, 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 right? You learn chemistry by doing chemistry, right? Not by just reading it, right? So you have to apply it. So you have to practice the things we've learned. I really like in the ebook, you can go through and, let me see if I can pull it up real quick here. Let me show you a couple things. I should have had this ready to go. In the ebook, you can find, shoot, this is not working. Give me 1 second here.
Is it the study area that you're trying to find?
Study area is another good place, but I was just talking about within the ebook itself. So from the mastering, you can go to Pearson eText, view the eText, right? Or if you have the printed book, you can do the same thing. But the nice thing about the ebook, let me just show you a couple things really quick. And this will help for studying. And the reason I like this is because it forces you to be active, right? Remember, passive studying doesn't really do you that much good. It does you a little bit of good, but really it's the active stuff that helps you, right? You got to actively recall, right? If you're trying to memorize a list of things, you can't just look at the list over and over. You got to cover it up and recall it, right? It's the recall that burns those pathways in your mind, right? And that's what you want to see. So let's see, we can go here. Yeah, let's just go here. Make that bigger. So if you go through the ebook, you'll find things like, here's an example, right? Unit conversion, okay? And then there are these 4 practice problems, all right? And these 4 practice problems are ones that you should try. The answers to these are in the back of the book in the appendix, but some of these, let me see if I can find one. Some of these are live. So the live ones are like the most important ones. And so you can at least do these live ones, right? So you might be looking through this chapter and say, aha, here's how I can practice. How many cubic centimeters are there in 2.11 yards cubed, right? So these kinds of 4 practice problems in the text, as you go through the ebook, read them and try them out and answer the questions. Why? That's active learning, right? You are actively involved in the process, okay? Another kind of thing you can also do are, let me see if I can find, as you go through the ebook, see, I'm running out of time here. There's these conceptual connections. Let's see if I can find one. There we go. Conceptual connection like 1.3. Again, this is active, right? You can, as you're reading through the book, you can go through this and say, okay, can I answer this question? And you'll get feedback. So the diagram below presents water molecules. Which of these best represents the molecules after they've been vaporized? Okay, let's say I push B. Oh, no, that's not correct, right? So it gives you feedback and it corrects your misconceptions. So that's another good way to help you study, right?
Yeah.
But at the end of the day, you want to be doing things, right? You don't want to just be passive in your study.
Yeah, correct.
Okay, good. Other questions?
Yeah, just because I'm a little nervous because it's like, what, 40-something questions in 1 hour. So I just wanted
Yes, exactly. So, I hate to put that time pressure on you, but that's the only way I can kind of control it in terms of, not giving people time to really cheat, right? You have your 1 page, if you're really well organized, put everything you can put on 1 page, right? One sheet, you can fill up both sides of the sheet. You can use all that information, but you got to make sure it's very well organized because you're not going to have a lot of time, right?
Yeah, correct.
Go to it quickly, right? So you're going to have to know the material well. Okay, I'm going to keep answering questions, but if you need to go ahead and go. Thank you for your attention. I'm gonna, I think I'll end the recording now, and I will stay around to keep answering questions.